These next two examples, I'm going to record these on the same video because they do use the same triangle configuration. And if you're looking at the three different triangles from the first page, they're both going to use the third one. The first one starts out as dx over the square root of 4x squared minus 49. We're asked to integrate that. It says that x is greater than 7/2, and that eliminates the possibility of having a 0 in the denominator. But I'm going to end up using, like I said, that third case. So let me draw out my triangle. So if this is theta, I'm going to have 4x squared, or the square root of 4x squared minus 49 is going to be one of my legs. If I take the square root of 4x squared, I get 2x, and that's the length of my hypotenuse. The square root of 49 is 7, and that's the length of my other leg. So now I've got my triangle labeled. In this case, I want to first solve for x, and the secant of theta is going to be opposite over adjacent, so it's going to be 2x over 7. And if I take this and solve it for x, I get that x is 7/2 secant theta. Remember, I'm solving for x just so I can find dx. So in this case, dx is going to be 7/2 secant theta tangent theta, d theta. So I've got that part taken care of. Now I'm going to deal with the radical. If I look at tangent theta, I've got the square root of 4x squared minus 49 over 7. And I can solve that for the radical just by multiplying both sides by 7. So the square root of 4x squared minus 49 is equal to 7 times tangent theta. So now let me go back up here, and I'm going to replace things. So instead of a dx, I'm going to replace it with 7/2 secant theta tangent theta d theta. And then in the denominator, I'll replace that with 7 tangent theta. The tangent thetas will cancel out. 7/2 divided by 7 is just 1/2. So I'm left with 1/2, and then I need to integrate secant theta d theta. Now, to integrate secant theta d theta, you're going to need to use the integral table, and you've got a copy of that in the Start Here module. We're going to actually use number 95 from the integral table to integrate this, okay? So I just want you to know I'm going to go kind of straight to what it looks like when it's integrated, but it's just, excuse me, allergies. We're just using number 95 again from that table. So I've got the natural log of the absolute value of secant theta plus tangent theta plus c, okay? And again, that came from that table. The only thing that I have left to do here is to go back and substitute for x. So secant theta is 2x over 7. Tangent theta is the square root of 4x squared minus 49 over 7. So we have 1/2 times the natural log of 2x over 7 plus the square root of 4x squared minus 49 over 7 plus c. And if you wanted to, inside of the natural log, or inside of the absolute values there, you could have written 2x plus the radical all over 7. I'm not going to take the time to rewrite it, but you could if you wanted to. So let's move to the second one here. So we're going to use the same idea here with the triangle where the radical is going to be on that vertical leg, but it looks a little different. So this one is asking us to integrate dx over x squared minus 1 to the 3 halves, and it says that x is greater than 1. And the x greater than 1, again, is just there to eliminate a 0 in the denominator. Now this one, let me scroll down here. I'm going to rewrite the denominator, and I'm going to write it as x squared minus 1 times the square root of x squared minus 1. You might be like, why are you doing that? It just makes it a little bit easier when we do our substitutions. Now, that square root of x squared minus 1, that's what's going to help me with the triangle. So like the previous example, we're going to have that x squared minus 1 on the vertical leg. Our hypotenuse is x, and then the other leg is 1. This makes things a little bit easier for us. So just like I did before, secant theta is going to be the hypotenuse over the adjacent side, so x over 1, which is just x. So knowing that x equals secant theta, I know that dx, the derivative of x, is secant theta tangent theta d theta. Additionally, tangent theta is equal to opposite over adjacent. So in this case, it's the square root of x squared minus 1 over 1, or just the square root of x squared minus 1. And if tangent theta is equal to the square root of x squared minus 1, then tangent squared theta is just equal to x squared minus 1. So now we can come back and substitute. What do we have? Well, dx is equal to secant theta tangent theta d theta. And in the denominator, the x squared minus 1 is tangent squared theta, and the radical is just tangent theta. So you can see that we can cancel out the tangent thetas. So I'm left with secant theta over tangent squared theta d theta. And there's different ways that you could go about approaching this. What I'm going to do is I'm going to convert my secant and my tangent into sines and cosines. So secant theta is 1 over cosine theta. Tangent squared, since it's in the denominator, we're going to flip it. So it's going to be cosine squared theta over sine squared theta. D theta. And that's going to allow me to cancel the cosine theta in the denominator with one of the cosine thetas up in the numerator, leaving me with cosine theta d theta over sine squared theta. At this point, I'm going to do a u substitution. So some of these problems, they're going to let you incorporate multiple techniques for integrating. I'm going to let u equal sine of theta, so that du is equal to cosine theta d theta. So I've got du over u squared. When I integrate that, I get negative 1 over u plus c. Now I'm going to go back. Since u is equal to sine theta, I've got negative 1 over sine theta plus c. 1 over sine theta is negative cosecant theta plus c. And then finally, I need to take this back to my x's. If I come over here to my triangle, sine is opposite over hypotenuse, so cosecant is hypotenuse over opposite. So I'm going to end up with negative x over the square root of x squared minus 1, running out of space here, plus c.